Okay, I think we're all set.
Yeah, okay.
Let's take it away.
So I wasn't entirely sure what I was going to do today. From the OPLSS course, I had two other sets of slides. One of them is definitely I didn't have enough time for. Although, yeah, I could squeeze a little bit in that in, and the other one is quite short, but follows on from what we were talking about. So I'm going with this one, and I'll probably show you some. I'll give you some live demos and see how they go. Showing you some code in Lynx and Frank, which are both programming languages I've worked on, very experimental programming languages with horrible error messages and that kind of thing. But so yeah, anyway, what I'll start off with is by just focusing a little bit more on the problems of effect typing for effect handlers. And I'm starting off with this claim. In order to support flexible composition of effectful programs, we need effect polymorphism. I've just added I've added an asterisk here. Well, I guess there's two reasons for that asterisk. A usual one that people often think they want and is necessary is well, maybe you don't need polymorphism over your effects. Maybe you just need effect subtyping. I'd argue that's not really true because, say, I take some higher order function like map. I really need polymorphism. I need to be able to say, well, I have a function that performs these effects, and when I perform them, well, I have the same effects. But the main reason for this asterisk is not that. It is the thing that Wen Hao, my PhD student, talked about in the lightning talks. He talked about some work we've been doing on modal effect types. Where we have shown that you can actually get almost the full expressive power of effect polymorphism, but without any actual polymorphism. And this actually, that observation dates back to much earlier work. It's Connor McBride's observation and the basis of the Frank programming language. But what we've done recently is shown that whereas in Frank, as I'll show you, there is some effect polymorphism there. It's just we have syntactic sugar that hides it in many cases. You can actually have a system that fundamentally doesn't have any. But anyway, I'm going to proceed on the basis that we do want some effect polymorphism. So using the similar syntax to what I've been showing you before, I gave you, these were a couple of the handlers we defined in the previous lectures. Maybe fail was one that takes a computation that has this fail operation and turns it into a maybe type. And when I showed it to you previously, I didn't write a for all here. I just wrote a capital E, meaning that was a meta variable. We could instantiate it with any effects at all. But here I'm saying we actually want to be polymorphic in those effects. And it seems a perfectly natural thing to do. And then similarly, another one I showed you is a handler for choice that returned a list of results. I'm not being polymorphic in whatever this type A is. I could be, but that's value polymorphism rather than effect polymorphism. But I am being polymorphic in the rest of the effects. And yeah, it makes sense. You want to do something like this if you want to have a program that has several effects and you compose the handlers together. You just instantiate these effect variables to make sure that the total effect is the combined effect that gets handled by all of the handlers. So we might, if I want to, actually, why don't I just show you the example? So assuming we have a system that has explicit type applications, we could, the two different ways I had of composing, composing these handlers together I showed you. Drunk tosses was a computation that it might fail and it might perform choose. So maybe fail definitely is going to be handling a computation that does the fail effect, but we need to tell it that, well, also it can do the choose effect. So that's what this is instantiating E with this effect here. But having handled all of this stuff, we've now consumed the fail effect. You see the fail disappears and you end up with E. So the thing you get back after that, the computation that starts with this parenthesis here, that just performs choose. So when we instantiate all choices, we can pass in the empty effect. If we do it the other way around, well, then you'd have to instantiate it like that. Is this clear to everyone? Any questions so far? No. Good. And I haven't really said what this thing means in this context, and it becomes important. So the basis for a lot of, well, not all, but a number of the practical effect type systems that people have built, including the ones in Lynx and in Frank, is row polymorphism. Roughly speaking, when you see one of those effect variables in a row type, it represents not the entire effect type, but some subset or some part of the effect type. So, like when we here, well, yeah, I guess that makes sense. We've got fail plus some other stuff. But still, there's a question of what plus means, which I'll come to. But the starting point is row types, which amount to type level maps from labels to some sort of type level thing. In the case of effects here, these are not actually, these aren't normal data types. They're the signature types. They're these things. But they are, rows were historically developed for other things. So for instance, this could represent a record or a variant. And the key, I guess, defining aspect of row polymorphism is that you can have the basis of a row like this, which says, I don't know why that should be a 1 and an n there. I don't know what happened there. But you have all these labels, and then you have a row variable, which represents a potential extension of that row with other things. And in our case, that was the effect variable. And you can only have at most one row variable in a row type, which is important when you do type inference to stop the constraints exploding. Not in most systems. You could decide to have a syntax where you did that, but that would just make your life harder. In fact, it is true that most systems do what I'm showing you there, where they stick the row variable at the end. Frank sticks it at the beginning, as Connor wanted to be awkward. That's not really true. There's actually there's kind of a reason for that. So yeah, originally row polymorphism was introduced for records, and as I said, you can also use it for polymorphic variants. It's like sort of extensible algebraic data types, and for effect polymorphism. And the labels we have here in our case correspond to, well, actually, yeah, that's true. Either operation names, which is what I've shown you so far, or actually in the case of Frank, and which is probably the right thing to do, you often, rather than having them represent just the operation name, they might represent a collection of operations denoting a particular effect. So you might, if you had a state effect, then it might represent that, where state has two operations, one for get and one for put. You could potentially have well, not necessarily that. So, for instance, in Frank, you can actually you can basically define an effect alias where you can combine as many effects together as you like. There's a choice, and in links, actually, these are structural. In Frank, they're nominal, or the effect interfaces are. The sort of implicit row types must be structural. Yep. Anyway, so I'm going to talk about this. There are a whole load of families of a whole load of variations on row polymorphism, but I roughly divide most of the systems into two categories. Remy style row polymorphism is one of them. And here, the intuition I like to have is that we view these rows as denoting maps from labels to type level maybe types. So each label is either present with a particular type, or it's absent. And you have to be a bit careful talking about this, because when I say present or absent, it doesn't mean this has nothing to do with which labels I write down in my syntax. It's what we're conceptually denoting. So if you have in mind this idea that, well, we're representing some sort of map, then that it's the map that either has them present or absent. Given this is a map, this is a function mapping labels to something, you're not allowed to have duplicates of these labels. But yeah, we'll see that the other form of row polymorphism actually does allow duplicates. So yeah, going back to those examples, in the Remy style, yeah, we as well as having, so I'm being hi. Do you want me to start again just for you? Or? That's fine. So in our types, we actually have three different kinds of things. We have our ordinary data types, we have row types, and then we also have presence types here. And maybe fail, so we're being very pedantic here. In an actual system, a lot of this noise might, with type inference, a lot of the noise might be omitted. So what does this say? We have an effect variable, which is a row variable. I have to list a collection of labels here. What this is actually saying is this is a row variable that ranges over rows that do not contain the fail effect, which might seem a bit of a weird thing to do, but you can kind of see why you might want to do that here, because we're using it in the context of an effect that does have the fail effect, and we've said you're not allowed to have duplicates, so E must not itself mention the fail effect, because we've already said that it has, well, this presence information. We can't say that twice. And then P is ranging over the presence information, so that's either going to say it's present of type A, yeah, which we often don't bother writing the pre bit, or that it's absent. Yes, there's something kind of interesting going on here. And this, you'll see, this is a bit painful. Yeah, so we've got E and we've got P, and we have a computation that returns a value of type A, and then we have the fail operation. I've been very explicit there and said, well, the kind of the data type that would get returned there is well, it's a data type. It's a type. And we might have some additional effects, but afterwards, those additional effects should be the same. And annoyingly, we still have to mention that fail here, because if we want to be able to use the thing polymorphically, well, it may be that we want to use this in the context that we might want to use this whole computation in the context of some other computation that also raises an exception, or it might not. So it's being very fussy here. And if you look at this case, it's basically the same thing going on. So the key annoyance is that we actually, not only do we have one effect variable, we also have a presence variable for each operation that we're actually handling. You could have a richer system that somehow allowed you to group these two things together. Anyway, there's any questions about this so far? Yeah.
I don't understand why you allow fail. For example, why we allow effective to handle a result.
Yeah, because we were being monomorphic. The main use of polymorphism with row typing and effect typing is to keep track of, that's kind of related to the frame rule in separation logic, all the other stuff you might want to compose this with. Now, supposing I write a program where I raise an exception, and then I handle that bit of code, then I have a program that has maybe A of whatever these other effects are. But I might want to raise an exception. I might want to compose that with another program that also raises an exception later on. And that's all that this is, that's what this possibility is about. And the reason we have to do it is because because of this constraint that you can only have one copy of each label in this row. So this E here, we know, says nothing about fail. It can't possibly say anything about fail because we've already said that fail is present. And similarly here, this one says nothing. This can say nothing about choose because we've already said that choose has this signature. So if we want to use it over here, we have to say something about whether choose is there. You could just put, oh, it's absent. And another thing you could do is if you combine this with subtyping, then that would be sound to do that. You could sort of say it's absent, and then you could upcast it to say if you wanted to use it in a context where it was actually present again. Does you understand what I'm saying?
You want to allow the possibility of using the same text
More than once.
more than one, and then one handle will just handle one of the.
Yeah. I mean,
Shallow handle might be correct.
no, it's not got anything to do with shallow or deep handlers.
But I want to see an example actually on the board. Otherwise,
Yeah, well,
I know what I'd want to do with the situation or describing. But I can't picture the product.
yeah, I guess I'll show some examples later, but possibly the a message I would get from this is that this is actually a pretty terrible way of dealing with effects, because you end up building up, having lots of type variables. Every time you potentially handle an effect, you have an additional presence variable, and you're basically saying, well, oh, possibly this thing is still here, and possibly it isn't.
So just to clarify, when you say row, like at the first effect variable, and then you say, okay, the row, type row, and it doesn't have to contain fail. Could I write that as fail colon?
So, I mean, I don't think I have the typing rules on here, but an important invariant here is you can only actually use one of these effects. Well, no. If I wanted to use this thing raw, or rather, if I actually, where do we use effects? We use them on the right-hand side of a bang. The kind of this is a good one to look at. Well, this thing has to be row of empty, as in I must have specified all of the labels in my row. So if I did the thing that I kind of want to do here, which is just not to bother writing that thing, then this would actually be ill-typed. You can only actually use a row if it's a complete row where you've specified everything about it.
And everything about it basically present rather than
for every label. And by default, if you can make the assumption that cofinitely many of the labels are absent. So a pure computation is just a row in which every label is absent.
So I could write equivalently here type row of empty, but before that fail colon absent. So fail colon absent row.
Yes. Yeah. If this thing here was empty, then I could write absent there. Although it'd be redundant. Well.
I'm just trying to understand.
No, sorry. No.
The type of the fail.
So actually, formally, you're not allowed to write that because, well, actually, that's not true. You end up quotienting the types. It's a bit.
Maybe it was your.
Yeah, do I? I don't think I have an example of that here, but I'll show you some code, which maybe we can. But the right way to think about it is that no, if you wrote E here and you wrote fail of colon anything at all, then E has to have a kind that says it doesn't talk about fail, because the act of writing down this map has told you something about fail. But
composing that one is
Yes.
It's fail on the right, it's red. Right?
Well, this is the whole point. This is like a sort of, it's an after image. We've handled a fail. We know that it's because we want to use this E here and here. We know that the E must not have a fail over here. And if we write it down again over here, then it also must not talk about fail. Therefore, we have to say, well, fail has some kind of presence information. We don't know what it is.
Oh, okay. I missed it.
Yeah, this is saying these are the things that are not in the row. It's an incomplete row.
No, it's the second parameter of the P itself. Which I've not.
Oh, you not.
I would have been happier with effectively presence. That makes sense. Which might not be well to me with a certain available syntactic sugar. It makes sense.
Sorry, what colon presence?
Fail colon presence as in fail if you don't have anything. That's it.
Well, but that's a type variable that ranges over that. The P. The P can be instantiated with either present or absent.
Yeah, that's why.
Okay, I'm going to.
It was backwards before.
I'm going to move on to the other example, which I think is probably a better way of dealing with effect typing. And from practical experience, it definitely works better. And but on the other hand, it's maybe seems slightly weird at first because, well, what does it mean to allow multiple labels in rows? But the way I like to think about this one is that what we're really denoting is a map from labels to type level lists rather than type level maybes. And if so here you have a weird situation where the syntax is such that the order in which you write the labels matters. In the other case, it doesn't. But here it does matter because, well, if you have two labels, well, which one is the first one or the one that actually counts? And in this case, it's probably more intuitive. You don't have any presence information at all. And so the kind of rows just says row. It doesn't need to list what's there and what's not there. And you, in this case, we start with an E and it appears on the left-hand side and the right-hand side. These are the effects that are not being handled. This is closer to what you probably want to write in practice. But it still does leave the question of, well, what's going on here when you have multiple labels? Right, and this is my initial point, was that this, when we have effect handlers support handler composition, right, oh, and okay, here's a somewhat concrete example. It's the example I showed you before. So now we, as well as having to specify the effects, you also had to specify what was going on with that presence variable. So one way of instantiating that presence variable was just to say, well, fail is absent. I'm just trying to remember. Right, yeah. And you see that the same presence, the same instantiation on both of the handlers. But otherwise, that's just what we saw before. Whereas in the line style, it's just, well, it's what we started off with. There is no presence information. And yes, this example shows you what happens when you're in a situation where you genuinely might want to do something like this. So this is an exception handler that takes. We're going to take a thunk, a computation that might fail, and then we're going to take this second argument, the h, is the code to invoke if we do fail. But again, the point is, well, it's possible that we want this thing to raise an exception itself, which is why we're polymorphic in whether or not it can raise an exception. And yeah, if in the case that h was able to fail, then we'd have to instantiate it with present to say that it's present and has the appropriate signature. Whereas in the Lion style, you don't do that. I mean, basically, we're just omitting any mention of fail after that. And I think this is worth noting. Going back to this dichotomy between either we have a map from labels to maybe types, or we have a map from labels to lists. The sort of fundamental algebraic property that explains why lists are more convenient here is, well, what are we doing? We want in the list case, well, this is basically just consing a new thing onto the front of a list, and you can't do that with an option type.
Lists, right? Or stats, matching the effect type. What's that?
They're lists. They're lists of types. At the level of types, they are exactly lists. But the point is, you can always con something onto the front of a list. You can't do that if you've only got one thing. You have to sort of decide, well, do I want to override it, or do I want to not accept it? Or well, okay, you could define a monoid over option types, but it's not as nice as lists. Oh yes, and I didn't tell you about the instantiation. So this is where it's a bit funny, because obviously, yeah, if h can fail, then we're going to instantiate e to some other to some effect that includes fail and then some other stuff. In fact, that doesn't have to be an effect variable. It could be a concrete effect. But that means that because we've got e, the e here says that we can fail and we can do whatever e prime is, but the e over here says, well, we can fail and then we can fail again. And yeah, as you say, Philippa, in a sense that you can think of that as capturing the stack of handlers. Yeah.
So does that mean that you could accidentally not handle all the fails, or you can handle it?
So in practice, in examples like this, you will notice. Let's see. Would you notice that?
If you try to write an effect type to a top level that said it won't fail,
you never actually write something of this type. We're not writing something of this type in this example, because the thing we're actually consuming this fail, the thing we're going to get out, is only going to have one fail in it. And the scenario we're talking about here is where M is probably going to be polymorphic in its, well, okay, it might not be, but you imagine M. All that we need to know about M in order to do the handling is that it has one fail, and it has this effect variable E. And it's only because we want to compose this with some other computation which may itself fail that we end up instantiating E to say that it has failed. In practice, you might see error messages with this kind of thing, but you don't normally write them yourself.
So if you do your typing right,
you don't have to name handlers, because you've got something like transactional.
You don't have named handlers, but you have names. You have a sort of de Bruijn-like discipline for referencing, and in fact, you can do this in Frank. You can actually deliberately say, I have a computation that has multiple copies of the same thing, and oh, I want to I actually want to handle this one, or I want to perform this one, the third one. But that's not really you're only really using this for the purposes of composition. So here's a point that applies to both of these. If we have higher order functions, something like map, for instance, in almost, I think, pretty much any standard higher order function you will find in say the Haskell prelude or most libraries, the effect variables are actually kind of redundant because, well, what do you do if you are passed in a function? You want to run it, which means that the effects it performs must be the effects that you get out in the end.
What if you're putting on handling yourself?
There are exceptions, but that they do not apply to things like map. So here are a couple of examples that, well, I showed you the first one, and map, you take in a function that may perform the effects at E, and when you run it, those effects should be performed. But we can, and this is essentially what the idea that Frank uses, you can adopt a convention where if you don't write down the effect variables, you just assume that all of the effect variables are going to be the same. So these notations here are intended to mean exactly the same things as these ones. We're not saying that this is pure. We're saying actually there's an implicit effect variable, but we're not going to bother writing it because it's always going to be this way that we want to use it. There is only one situation in which you would want to do something different, and that is where you have a function, well, where you're essentially storing your function for later use in a different effect context. Otherwise, this is always what you want to do. Yeah, okay, so you can go one step further, and then we get to this nice situation where the signature of map just looks like the pure signature of map in a pure functional language. But it doesn't actually mean that. Yeah. So if you still want to be able to explicitly say, oh, this thing is pure and it cannot be instantiated, then if you use this notation, then you need a way of explicitly saying that. But yes, I'm claiming this is probably true, that mostly when you're programming with row types, this is, yeah, your polymorphism kind of pollutes everything because that's really the way that row typing works. You're sort of saying, well, oh, I might want to compose this with something else, so I'm going to leave open the possibility that I could add other things. You don't very often want to do this. All right. I'm realizing this was taking. I didn't have many slides, but it's taking longer than I thought it would, which is maybe good. So I'm wondering what I'm going to have time for here. I think I do want to. I want to show you this example. This is an example I showed you before. But now we've talked about what effect polymorphism is, it's going to make a bit more sense. So this is where we want to compose together essentially two handlers. We have a computation. We have one effect which is reading, a get operation. But the way we want to implement reading is, but we're going to take a list of natural numbers, and we will just read the next natural number until we run out of natural numbers. And at the point at which there are no natural numbers left in the list, this is a parameterized handler. threading through this list. If that list is empty, then we actually fail. Otherwise, we just return the number and thread the tail through. And then we have maybe fail, and you'd hope. You'd hope that if you'd have some way of composing these two things together so that you can specify a computation that does not necessarily perform the fail effect. But internally, we generate the fail effect and then consume it. So you can see it's introduced here, and it's going to be eliminated here. I'm using the convention that I'm effect polymorphic. So I'm using the convention from the previous slide. So there's actually an effect variable here, which means that when we compose it together, it will get instantiated with fail. This is why we wanted the effect polymorphism. So, but you're absolutely right that when we come to actually, well, so this reads handler, it will handle get, and anything else that it gets will get passed through. Oh, yeah, you're right. No, there should be a fail here. Yes, sorry. I had the same typo on when I showed it earlier. So that must have been a copy and paste error from somewhere. Right, I should fix that. Yes, sorry about that. Yeah, and that would make more sense because yes, we start with get, we're going to have fail here, and then we're going to have the fail going to nothing. But if we actually compose these things together, if I write that, this is basically the idea of what we wanted to do. We wanted to take a computation, handle it with reads, and then with fail. You end up actually having to give it a type that looks like this, where we're mentioning fail here. This is absolutely the thing we do not want to do, because fail is just it's an implementation detail. Reads produces fails, but they immediately get consumed. And this is not just a typing issue. This is actually about the semantics of the program, because, well, what does maybe fail do? It will take any fail it sees. I haven't exactly specified which kind of effect type we're using here, but we'll get to that. It doesn't matter which one you're using. You still have this problem. And in particular, if I run this computation, what we should have happen here is the reader is being handled by generating fails, which then get turned into nothings. But this fail should not be handled. We should actually get an unhandled. The type we have here should not be maybe nat. It should be maybe nat that may perform a fail, meaning that you need another handler around it to handle that. So the question is, how can we encapsulate this? And what we're trying to do is define a function that does not mention fail here, but still gives you something pure at the end. So I showed you that problem before. And that there, you see the fail effect should come out there, and this will actually perform an unhandled fail operation. And the solution that you can do in the line style, which essentially Frank does, is you introduce this notion of masking of the effects. And it's sort of analogous to weakening on the level of effects. So at the point at which we run the computation, we say, well, actually, we want to, because we're using fail internally here, we want to hide it. And then you get exactly the right behavior. Another way of doing it, and if you think more about this, you'll realize, well, what's the fundamental problem here? The fundamental problem here is that we have these names, these labels, but they're not first-class things. They're just globally fixed. If you start composing things together, that's disastrous. So if you add a way of generating a new label that's guaranteed to be fresh, then you can use that internally for composition.
You don't want typically like that's right. Then
Yes, exactly. You can have some way of doing that. So you can have effect instances. Actually, various versions of the F language have this, or don't have this, because Mattia keeps adding and removing facilities. But it all boils down to just names. Now what? Right, and you can add a typing rule that just adds an extra copy of op. Okay, how much? No, I don't have much time. So I'm going to just say a little bit about, well, Frank and links, and if you want me to demo things, I can do that later, because I don't think I have much time. So these are all quotes that come from, well, I think they were all sourced by Connor in our paper on Frank. The name of the original name of the paper was Doobie Doobie Doo, and hopefully you can work out the etymology of that from this. Doing and being is a fundamental aspect of it. The journal version has extra O's and E's in it because the original version is not indexed by Google because it consisted only of 2-letter words. And this one is. And do is a Scottish word for dove. So I guess this is about animals. I think both titles are terrible because they don't really tell you, unless you are Connor and know what the in-joke is, what the paper is about. But it was fun anyway. Right, there should probably have been a subtitle that explained what it was about. So yeah, Frank is sadly not very well. We've not really made any changes to it for years, but it is very much an effect handler oriented language. Embraces for them from the start, and it has some of the features I've shown you already. So the invisible effect polymorphism is certainly fundamental to it. You, in practice, very rarely need to write any effect types at all, but there are some you can if you genuinely want to be able to store an effect and store an effectful computation and use it in a different effect context to the one you're running in. It has an unusual evaluation mechanism. It's a bit like call by value. I call it call by handling. So handlers and functions are actually conflated with the same thing. A handler is a generalization of a function. If you just pass in a normal value, so yeah, basically a handler that does not handle any effects is just a normal function. So you can think of the return clause as specifying the body of the lambda. But if it does handle something, then when we pass in an argument, we're not passing in by value, we're passing in a computation. And whenever that computation performs an operation, it then has a kind of dialogue with the handler. This is something I would probably have to illustrate with examples, and I don't have time. But it also has multi-handlers, which means that you can handle multiple computations at the same time. And this dialogue that's going on allows them to synchronize. So the Unix pipes example I gave, for instance, you have a send and a receive, then you can write that very concisely in such a way that they get together. It also has another innovation, adjustments. So rather than talking about the whole row of effects, it tells that these describe how you transform the effects. And it reduces the need for polymorphism further. But again, I don't have time to talk about that. And an instance, the adjustments can either talk about extending your effects, or they can talk about restricting them or rewiring them. And there are these things called adapters and masks that I showed you as an example of that. But really, these are they correspond to what Connor calls thinnings, so context morphisms. So you can imagine you might want to swap certain effects, or if you've got one of these lists, you might want to swap the order, or you might want to duplicate them, remap them. And that turns out to be occasionally useful, but mask is the one that's most useful for composition. Its main misfeature is it has very odd syntax where it looks like you're writing curried functions, but they're not, they're n-ary functions. I'm going to briefly mention links. You have this nice slide that Simon Fowler did. So links is a research language, web programming language that Phil conceived. Phil Wadler is there about 20 years ago nearly. And it's had all kinds of research on it, and we realized a few years ago that it had a whole load of the ingredients we needed to implement effect handlers. It had row types, it had continuations, so we just did it for fun. And I was going to demo stuff, but I'm not going to because I've run out of time. But if you want me to do that later, then come and talk to me. I guess I'll finish with this slide, which mentions some of the challenges to making effect typing work in practice. I've talked about effect encapsulation. We had a POPL paper this year on combining linearity with effects. And the problem there is if you can duplicate continuations, most linear type systems are normally defined under the assumption that that does not happen. So there was a soundness bug in links, which we fixed by working out how to combine these things. And you need to track which, you have this notion of control flow linearity. Generativity is something I also alluded to, so generating fresh effects or fresh names can be important. Indexing of the effects is something that can be very powerful. And there's still kind of quite a bit of ongoing work there on how to do that nicely. But and then equations, bringing equations back into the picture. I started with those right at the beginning, but yes, we might actually still want to be able to reason about our effectful programs inside the system, but you need to.
I think that's a very good advice. It's still going much longer.
It is. It isn't on the hour thing. Yes, I think, but it is a sign that I should stop. So I shall stop.